Hello, I'm Cameron Mitchell, and this is my Calculus and Vectors CCT. The page that I will be doing my problem from is page 275, number 15, question A through to question D. Question 15 tells us Evangelista Tortellini developed a formula for calculating the barometric pressure at various altitudes. The altimeter of an aircraft uses a similar formula to determine the altitude of an aircraft above sea level. The formula has the form P equals 101.3 e to the exponent negative k times h. For the atmosphere at the standard temperature and pressure, where P is the barometric pressure in kilopascals, H is the altitude in meters, and K is a constant. 15a tells us if the barometric pressure at an altitude of 1,000 meters is 95.6 kilopascals, determine the value of K. So here we have our completed question and answer. We're going to go through each step to get a greater understanding of how we came up with this number for K. First, we want to write down our givens. We know the altitude, 1,000 meters. We know the pressure, 95.6 kilopascals. And we also have our equation from our number 15 explanation, which is right here. Now we can sub in values to find K. Here we have 95.6 kilopascals and 1,000 meters. Now we want to begin to solve for K. So first we're going to get rid of this. We do this by dividing as shown here. Now we run into a little bit of a problem. Right now, K is in the exponent, and we want to bring down K. To bring down K, we must be able to recall properties of a logarithm. Now, properties of a logarithm is one of them is this: log b to the x equals x. Now we're going to have to change this around because our base is e, Euler's constant. So we're now going to rewrite it as this: log e, Euler's constant, to the x equals x. Now, because we have Euler's constant here below, we can use ln, and ln is the inverse. So ln e x equals x. So what we're going to be doing is taking the ln of each side to get K down into the base. And then it won't be an exponent, and we can easily solve for K. So that's what we've done here. We've brought K down, we've divided by negative 1,000 to get rid of the negative, and here we come up with our value for K. We then must include a therefore statement, and the therefore statement answers the question that was asked. What is the value of K? And the value of K in this case, which is a constant, is 5.79 times 10 to the negative 5. Now we move on to question B. Question B is asking us to show that the value of K from part A correctly predicts a pressure of 90.2 kilopascals at an altitude of 1,000 meters. So we're given our altitude, 2,000 meters, and we're given what we want to find, the pressure. We want to be able to get a pressure of 90.2 kilopascals. So we rewrite our equation. we now have the value for K. We now have a value for H, so we're going to go in, sub these values in, to find P. Here we simply punch these numbers into our calculator to get a value of 90.22 kilopascals. This is approximately, and rounds to, 90.2 kilopascals. Once again, we include a therefore statement. Therefore, the value of K determined in A is correct, as we have gotten a pressure of 90.2 kilopascals at 2,000 meters. So now we've completed 15A and B. We're going to be moving on to 15C. And 15C asks us a different question. It's asking us the vertical speed indicator of an aircraft uses the change in barometric pressure with respect to time to determine the rate of climb of the aircraft. Determine the first derivative of the barometric pressure formula. So here we're not really given anything. We're given the original equation, and it's asking us to take the first derivative. And this first derivative will give us the rate of change of the aircraft from pressure with respect to meters in this case. So here we have our original equation, right here. It's asking us to take the derivative. Now, in order to take derivative, we have to be aware that this is an exponential function. So this can be rewritten as e to f at x. Now, to take the derivative, we have to be aware of derivatives of a power. Now here, because we have Euler's constant, we're going to keep this the same. Keep this the same. But we're going to take the derivative of this. And this can be rearranged to then this. That's our goal in this question. We want to find the derivative. So as seen here, we keep the same. And then we take the derivative of this. Now, here we have h, but we don't have like a cubed or a squared to the h. It's simply 1. So we multiply this by 1. And this then, 1 minus 1 equals 0. H to 0. So this disappears, and that's all we have as our derivative. We then bring it up to the front, and we get this answer. This is our derivative of the barometric pressure formula. Now, question 15D is going to be asking us to use this derivative, rate of change, to determine the rate of change of the pressure with respect to height at an altitude of 1,500 meters. So right off the bat, we're given the units in which we're finding it in. And it's going to be kilopascals, pressure, with respect to altitude, which is meters. So we want to keep that in mind. These are going to be our units. Next, we're given the altitude, and it's 1,500 meters. So we take our equation of the derivative that we found in 15c, sorry, this is long. Oh my gosh, what did I do here? And now we can sub in our values. So we're going to go ahead and do that. Now we can plug this into our calculator and get the rate of change of the barometric pressure with respect to altitude. And we get negative 5.38 times 10 to the negative 3, using the units here, kilopascals per meter. So therefore, this means that the rate of change of the pressure with respect to altitude is negative 5.38 times 10 to the negative 3 kilopascals per meter at 1,500 meters. So this is telling us at every meter the pressure is decreasing at 5.38 times 10 to the negative 3 kilopascals at a height of 1,500 meters. Now that concludes 15. And what we can see is that calculus is used in daily life for many applications of work. In this word problem, we can see it being used in aircrafts. So calculus can be applied to anywhere in any job that we may undertake. Thank you very much, and this is the end.